Today we're going to be talking about numbers. Now, here is an alphabet, a certain collection of symbols that we most commonly use to represent numbers. It's called a base 10 number system. So in a base 10 number system, I can represent any number as some decimal expansion. Let's look at the number 2317.19. So this number can be written as 2 times 1000 plus 3 times 100 plus 1 times 10 plus 7 times 1 plus 1 times 1/10 plus 9 times 1 over 100. Okay? And so in general, any decimal expansion of a number can be unpacked in the following way, where we're grouping a certain length. Let's say if I'm just looking at length here, I have some unit of length, and then I'm splitting up that unit of length into 10 pieces. Here's like 1 times, 2 times, etc., all the way up to 1. And the idea is that any arbitrary length, as long as I do a fine enough scaling, right? As long as I scale, if I split this now length scale up into tenths again, and I look at 1/100ths, then I'm going to have more accuracy with my measurement system. And essentially, I can measure any length up to arbitrarily high accuracy by just expanding far enough down the decimal line, okay? But we don't really know, what about an infinite decimal, right? Like, what about a decimal that goes on forever? Okay, so maybe you could think of this as representing some real physical length. If you believe that the real numbers truly represent reality, then this could be the true length of some quantity. And then I might ask, okay, if I measured this length, maybe I'd get a measurement that cuts off at this decimal, so I'd have this much accuracy in my measurement. You might ask me, well, what does it mean for the decimal to repeat on infinitely? Okay, so before we talk about that, let me just quickly mention that we have a notion of we have a notion of addition, subtraction. Okay, these are between numbers in the base 10 number system, and we also have a notion of multiplication. Now, intuitively, addition and subtraction come from a notion of length, geometric length. So, for example, if I have two numbers and I add them together, let's say x and y, then if I add them together, I'm going to get a total length x plus y. Okay. And then if I wanted their difference, the difference in these two lengths, then intuitively speaking, now these are of course positive numbers. I mentioned that x and y are positive numbers. If I want the difference in their lengths, okay, then I put x over here, and this distance is x minus y, okay? So addition and subtraction have a very geometric foundation with the notion of length. And then multiplication then is passing from length to area. So if I have x and y are the lengths of a square, then the area of this square is x times y, okay? All right, we know how to, well, hopefully you've learned, or if you haven't, that's okay, but there are ways to multiply two numbers and add two numbers in the decimal system. So for example, if you gave me 2,345.17 and asked me to multiply it with 329.21, I could perform this multiplication, and there's an algorithm for doing this, okay? And there's also an algorithm for adding and subtracting numbers in this base 10 number system. Okay, so where am I going with this? Well, if we look at multiplication and we look at the square with side lengths of 1, and I ask the length of this diagonal, okay? And I want the length of this diagonal. Okay, well, it turns out the length of this diagonal is square root of 2. If you apply Pythagorean's theorem, we have 1 squared plus 1 squared is equal to square root of 2 squared, okay? So the length of this diagonal is square root of 2. Now the question is, can this length be represented as a decimal expansion in this number system? And, well, it can, but it requires you to use an infinite decimal, okay? And an infinite decimal that is aperiodic, that never repeats itself, okay? So in particular, square root of 2 cannot be written as a fraction, or cannot be, the information in the square root of 2 cannot be fully captured in any finite length word in this number system, okay? Now let me unpack what I'm trying to say a little bit more clearly. If I instead looked at something like 1/9. What is 1/9? Well, 1/9, you could think of it, or actually, let's do 1/7 for clarity. Okay. So 1/7, geometrically speaking, I'm simply taking a line of unit length and splitting it up into 7 pieces of equal length and asking what is the length of each one of these pieces. Okay, now if we use the division algorithm to calculate this, then what that would consist of in a base 10 number system is I'm essentially going to divide 7 into 1, and I basically expand 1, I cut 1 into 10 tenths, I cut it into 100 hundredths, into 1,000 thousandths, etc. So if I cut 1 into 10 pieces, each of size 1/10, then 7 divides into this, and I'm left with 1, then I subtract 7 here, and get 3/10 remaining, and I split the 3/10 into 30 hundredths, and I'm going to get 4 here, 28, 20, and then if I keep doing this division algorithm, I'm going to get 2 here, 14, 6, got another 0. Now I have, 60 10 thousandths, and I'm taking as many pieces of 7 as I can from that. And now I have 8 pieces I can take, 56, 4, 40, continuing addition over here, 40, just for, 40, I can go in 5 times, 35, 5, 50, I can go at 7 times, the 1. Okay, so now I've gone back to a 1, and now if I go do 1, 0 here, if I keep dividing the 7 into 10, I get 1, and then I'm going to repeat the same process. And notice that I've now reached a point in my division algorithm where my numbers start to repeat themselves, okay? So once I achieve the same, if I do the division algorithm and I either achieve a remainder of 0 or achieve a remainder that repeats itself, for example, the number 3, we could say, repeated itself, okay? Then what's going to end up happening is my decimal is going to start repeating itself. 1, 4, 2, 8, 5, 7, okay? So, in fact, even though that 1/7 is an infinite decimal in a base 10 decimal expansion, the information can be perfectly captured in finitely many digits, and then I specify these finitely many digits are repeating themselves periodically, okay? So I can identify a pattern of this repeating sequence of digits. It turns out that every fraction has this pattern, okay? Every fraction has a periodic decimal expansion in any number system. It doesn't have to be base 10. It could be any base number system. If I look at a fraction, its decimal expansion will be periodic, okay? And so the proof of that is essentially a pigeonhole principle, where I only have the amount of remainders that if I do this division algorithm, the amount of remainders that I can have is a finite number, because every time the remainder has to be less than this number 7 here. So each time I do the division algorithm, I'm left with a number that has to be less than 7, but if I do the division algorithm infinitely often, I'm going to eventually repeat myself, right? Because I only have finitely many choices to exhaust before I'm forced to repeat myself. And at which stage, if I ever repeat myself in this division algorithm, then I'm going to force to be having a periodic decimal expansion, okay? So every fraction has a periodic decimal expansion. So it turns out that the square root of 2 is not equal to a over b for any choices a and b. Doesn't matter what numbers you choose for a and b, you can not write square root of 2 as a fraction. Turns out that square root of 2 is actually an aperiodic decimal expansion. So if I look at the decimal expansion of square root of 2 and I expand it out, it'll never repeat itself. Same thing with pi, okay? Pi is 3.1415, et cetera. Okay? So this number, if I keep going out all through the decimal expansions all the way up to infinity, I'll never find a perfectly periodic string of numbers that repeats itself on and on forever, okay? And in fact, most numbers are like this. Most numbers is actually a very structurally rigorous. It's a large limitation to put on a number to require that its decimal repeats itself periodically all the way up to infinity. That's a large limitation on a number, and so there's actually, intuitively speaking, less fractions than there are real numbers. Okay, but we'll get into this rigorously in a minute. So I need to somehow pass. The goal is to pass from a notion of fractions okay, which we call rational numbers belonging to the set Q, we want to somehow pass to the notion of real numbers, which is somehow the notion of, you know, of any number that can be written as essentially an infinite decimal expansion. Okay, so the real numbers is basically I allow all decimals, including aperiodic decimal expansions. Here, the rational numbers, all the fractions, are going to be good approximations of the real numbers, but this is actually a very small subset of all the real numbers. Namely, this is the subset with only periodically repeating decimal expansions. Now, I will note that any real number can be approximated, again, to an arbitrary degree of accuracy by a fraction. Namely, if I cut off at any point this decimal expansion, I get a rational number on this side. So if I want an arbitrarily good approximation of this real number by a rational number, I just cut off at far enough along as far down the decimal to the right of the decimal as I need to any arbitrary degree of accuracy. So in this case, it's a 1/10, 100,000, 10,000, 100,000 million. So this is going to be within a 1/10 million or 1/1 million accuracy. Okay, so it's plus or minus 10 to the minus 6, which I believe is 1/1 million. Okay, so basically we're gonna need to look at the passing from the rationals to the real numbers. That's what we're gonna do next.